In this clip, we will take a closer look at the data structure called linked list. C# and Java both provide linked lists via the built-in type linked list. C++ provides it in std_list, and in Python, I think the type that comes closest is collections.deque. The backend data structure for dynamic arrays and many other data structures for that matter is a static, sequentially stored array. In linked lists, however, the individual elements are stored independently as isolated units. Around each element is a small container with a pointer to the next element. Often there is also a pointer to the previous element, and in that case it's called a doubly linked list. So this is basically the structure, and in principle we could stop there. However, the chain is often associated with an entry point container that holds a pointer to the head and the tail element. Let's do some complexity analysis and assume that the chain contains n elements. First, getting the head or the tail element is easy. We just follow the respective pointer and notice that this pointer following is independent on how many elements that are linked together. In other words, getting the head or the tail element only takes a constant amount of time, that is, big O of 1. However, in order to find a specific element, the chain needs to be traversed, possibly to the very end. So finding a specific element takes big O of n time. Remember that the individual elements in the linked list are stored in a small container with links to the next and possibly previous element. Assume that we have traversed the chain by following these links and ended up at the container holding the value 12. If we would like to insert a new element after 12, it's just a matter of adjusting the pointers, but before we do that, notice that we can reach the pointers at the element 34 in constant time, just by following a single link. So inserting a new element after 12 here is just a matter of letting the 12th element point to, in this case, 235, letting 235 point to 34, and the other way around. Again, the complexity of this operation is completely independent on the number of elements in the chain. It's always just a matter of changing 2 pointers, or in case of a doubly linked list, 4 pointers. Therefore, inserting an element into a linked list, provided that we have already found the element to insert from, takes a constant amount of time, or big O of 1. Now, consider the element 73. Deleting that element is just as simple as inserting a new element. We just need to let the previous element and the next element reference each other instead of 73, and we are done. Like before, this is independent on the number of elements in the chain, and thus removing an element is also big O of 1. Let me briefly add a few comments to linked lists. Notice that we can merge 2 linked lists in constant time independently of their length. This can be done simply by moving a few pointers. We saw that it took big O of 1 time to both add and remove elements, and there are no reallocation of the remaining elements when performing these operations. And this makes linked list ideal for example, queues. We simply add elements from the head of the chain and remove from the tail, or the other way around. Another benefit from linked lists may be their independence of pre-allocated continuous storage. Instead, we can just add elements one at a time until storage is completely full. Be aware, however, that the access time for elements that are scattered around in the storage is larger than the access time for elements in arrays that are stored in a single continuous segment. Also notice that the storage overhead used for storing pointers may be significant if the data type of the linked list elements is small, such as integers. Let's do the first adjustment to the investment analyzer and use a linked list as first in, first out queue in the stock trader. I'll head over to Visual Studio and alter the source code. Here we are in the stock trader. And as you can see, we used a list for the stocks to trade queue. Before I change this to a linked list, let me head over to our main loop of the program. Here, remember that we only send investment queries to the stock trader subsystem in case they have gotten a rating of at least 80. If we scroll down here, you might remember that we were creating 100,000 queries that was put through the pipeline, and only a subset of them ended up in the stock trader. In order to really show you a performance difference, I wanted to put some more elements into this stock trader queue. So I have inserted a small chunk of code where I now insert 200,000 elements in the stock trader queue, and then ask the stock trader to handle these 2,000 elements. So first we enqueue 2,000 elements, and next we dequeue them. In the first implementation, we use a list as you saw. Let me first try to execute this small test. There, 11.51 seconds. Let me go to the stock trader again, and instead of using a list, I will use a linked list. And also I will make an instance of a linked list. So now that I have changed the data type, I will need to change the method that I call on this data type. A linked list in C# does not have an add function. Instead, I will use add last. So this means that I will put this query to the tail of the chain. Also, I need to go to the handle tradings method, and instead of accessing an index directly, I'll just call the first property, which returns the first element of the chain. So I am adding to the last element of the chain and getting from the first element of the chain. And instead of removing a specific index, I will call the method remove first. So this was all I wanted to do, and now let me try to hit the experiments once again. Whoa! Handling these 200,000 stocks was now done in 0.01 second instead of the more than 11 seconds from before. Now let me try to execute the investment analyzer pipeline once again, but now with a linked list instead of a dynamic array. So querying all the queries was done quite fast, but analyzing the queries still takes a considerable amount of time. I'll pause the video and come back once it has completed. So 111 seconds. We saw a significant execution time reduction for when we considered the queue alone and changed its backend data structure from a dynamic array, a list type, to a linked list. When considering the complete run of our investment analyzer, however, the execution time went from 117 seconds to 110 seconds, which is still very large, considering that we are only measuring the investment analyzer framework. Hopefully we can reduce it even further with the help of some other data structures.